In this video, I want to introduce the idea of a vector. And a vector is a directed arrow line segment with an initial and terminal point. And what a vector is trying to show are two things. One, it's trying to show its direction, where it's moving or where it's going, and also its magnitude or the length of its vector or how far it has traveled. And so vectors have a lot of applications in both math and in physics because it is a way of indicating those two things, direction and magnitude. And oftentimes you will see vectors drawn on a Cartesian plane. And so you will see vectors in space on a Cartesian plane, and you'll see their initial and their terminal points. And these points are often described by what's called their components. A couple of notation things that you should know about vectors. Oftentimes you'll just see vectors written or notated just by some variable like u or v. If you see this arrow symbol on top of a variable there, that's just to indicate that it is a vector and not a line segment or a ray. And you can see here in the diagram that a vector has, again, an initial point and it has a terminal point. And we can describe that vector from the points where it's starting and where it's ending. So we can call this vector here vector PQ. Or again, you could label it some other variable here, like just saying u, with or without that vector notation on top. As I mentioned before, vectors are often drawn or written as being within the Cartesian plane or on a coordinate plane. When the initial point of a vector is at the origin, then we say that the vector is in standard position. So any vector whose initial point is at 0, 0, or the origin, we would say that that vector is in standard position. When a vector is in standard position, we can often just express the vector by its terminal points. So for example, again, if I were just to draw a vector somewhere here with its initial point here at 0, 0, and wherever this terminal point might be, let's just say, for example, it's 4, 2 here, we can say that this vector u, or vector, let's just call it v just to be consistent, we can say that vector v here, we can describe it in terms of its terminal points. So we could say something like 4, comma 2 here. And when we're describing vectors and the components of vectors, we often use these symbols here just to indicate that we're talking about a vector. If we said just 4, 2 with parentheses, then we would be describing a single point. But with those kind of arrow braces there, it's to indicate that these are the terminal points of our vector. And when you have a vector that's written in this form, we say that this is component form. So the component form of a vector is when a vector is written with its initial point being at the origin and described just by its terminal points. Now, any vector that is not in component form, we can write it in component form by rewriting it as if it were in standard position. And all that is simply finding the difference of your x components and your y components. And we'll do an example of this below. But just making sure that we understand what we're describing here, these are our components of our vector. A few other miscellaneous things that we should know about vectors before we try some of these problems. One, when both the initial and the terminal point lie at the origin, this is known as a zero vector. And so we often just denote a zero vector as what you're seeing here. And in terms of some basic vocabulary, just understand that when we're talking about a vector's magnitude, that's just another way of describing the length of the vector. And the notation for the magnitude of a vector is the following. We would say something like this here. So when we see that, then we're describing the magnitude of a vector. And if you think about the magnitude or the length of a vector, how else in math so far have we found the distance or the length of a particular line segment? Well, we've just used the distance formula. And so if you keep that in mind, then we can see easily that the formula to find the magnitude of a vector is just the square root of v sub 1 squared plus v sub 2 squared. Again, it's just the distance formula. I should write that, the distance formula. Now, a unit vector is simply when the vector's magnitude is exactly equal to 1. When we have a vector whose magnitude is 1, we call that a unit vector. So let's actually just dive into some problems because I think it'll help us understand some of this terminology a little bit more easily in its applications. So we have two vectors here. We've got vector v and vector u. We could also describe vector v as being vector rs. That's one way of describing it. And similarly, we could describe vector u as being vector pq. Now, take a look at these two vectors and ask yourself, just as a review, which of these two vectors are in standard position? If you said vector pq or vector u, you would be right. And since vector u is in standard position, we can write vector u in component form. We could say vector u or vector pq can be described in its component form because it is in standard position, 3, 2. Okay, so that was pretty easy to do for vector u because vector u was already in standard position. We could say that vector u's component form, so I'll do this for part A, vector u's component form was equal to 3, 2. Now, vector v, on the other hand, is not in standard position, but we can still write vector v in component form. So for vector v, to write it in component form, what we would want to do is the following. We would say, all right, what is the difference of the x components? So in other words, if we look at 4 and 1 here, we would say 4 minus 1. And then what would be the difference in the y components? 4 minus 2. So we can see that vector v in component form would simply be equal to 3, 2. You'll notice now that both vector u and v have the same component form. Well, what exactly does that mean? Well, if two vectors are in component form, have the same component form, then means two different things. Number one, it means that their magnitudes must be the same. So again, if I wanted to find the magnitude of vector u, then we can just apply the distance formula for vector u. So this would just be 3 squared plus 2 squared, since we've already found that in component form, and that would be equal to root 13, or radical 13. If I wanted to find the magnitude of vector v, and pretend that for a moment we didn't already write the component form of this, which we already know the component forms are the same. But we could also say something like 4 minus 1 squared plus, let me just extend that out, 4 minus 2 squared. And this would also give me 3 squared plus 2 squared, which is radical 13. So two vectors right now that have the same magnitude. The next thing we'd also want to show is that their angles are exactly the same. We haven't discussed that yet, and we won't discuss that for a little bit, so don't worry about that right now. But just understanding that two vectors that have the same component form, we would then say that these two vectors are equal to one another. So vector u and v are equal. Were they both in standard position? No. But if you were to move vector v into standard position, in other words, if you were to take this vector here, vector v, and just transpose it right here with its initial point being at the origin, you would see that both of these vectors have the same length and they have the same direction. And we know that because they are both ending, or its terminal point is the same spot. Both of these vectors are ending at 3, 2. So therefore, we would say that these two vectors are equal. So pause this video and try these practice problems that you see here, and go ahead and check your solutions with the ones that have been uploaded to Google Classroom. If you've had a chance to check your solutions, now let's move on to doing some basic vector operations. So what this means is we can actually add and subtract vectors. We can't quite multiply vectors together. We can do something like finding what we call the dot product of two vectors, which we'll discuss in a later video. But what we can do, however, is multiply a vector by a scalar, which I'll discuss in a second. So let's go through these bit by bit. So first off, there's vector addition. And what this means here is if I were to have vector u, and let me just go ahead and draw kind of an arbitrary vector u. So suppose vector u looks something like this, and I'll indicate this is our vector u with my vector notation. That's pretty terrible right there, but let me just go ahead and fix that. All right, so let's say that's vector u. And vector v, let's just do this in a different color, something like this, vector v. If I were to add vector u and v together, when we're just finding what the resultant vector is, we can just go ahead and add the x components, add the y components, and we will get our resultant vector. Graphically, what would that look like to add u and v together? Well, graphically, what that would mean is effectively from the tail end or from the terminal point of vector u, you would then draw or transpose vector v. Essentially, what that means is you're treating the tail end of vector u as if it were the initial point of vector v. And then you would just go ahead and draw vector v, something like that. This is vector v right here. And the vector that starts from the initial point of u and ends at this terminal point of vector v, this is what we call our resultant vector. This is u plus v. And I'll just label that. This is what we call our resultant vector. Now, vector addition is commutative, meaning u plus v will give you the same resultant vector as v plus u. So what I would do there is I would say from vector v, I'm now going to go ahead and draw vector u. So again, same process. From the terminal point of vector v, I'm now going to draw a vector u. And this vector should have the same terminal point as the other resultant vector. They should all end up in the same spot. You'll notice when I did it this time, I went ahead and I did a dotted line for vector u. And this is pretty similar to whenever we graph functions. The dotted line is really just meant to guide us and give us a sense of where our vector is going to be. You don't have to draw everything with a dotted line, but what is going to be important then is that you label all of your vectors. So either one of these two forms of drawing either a dotted vector or a non-dotted vector is fine, but just make sure that you're labeling all of your vectors so that you are indicating which one you know is your final resultant vector after I've added them. Okay, now let's try an example of vector subtraction. So vector subtraction is going to have a pretty similar process. So let me go ahead and start with similar vectors here. So let me again draw something like vector u. So here's vector u, and then draw something like vector v here. So those are my two vectors. Now, what we're going to do when we draw vector subtraction, again, mathematically, to find the resultant vector, you can just go ahead and you can subtract your x components and subtract your y components. And that end result will give you the component form of your resultant vector. And I'll do an example of this in just a few minutes. But graphically, what does that look like? Well, before I show you graphically what u minus v looks like, it's important to note that whenever we have something called a negative vector, it means we are going to flip the direction. In other words, and I'll do this in pink, what would negative v look like? Negative v would look something like this. It's our way of showing that we've got the same vector with approximately the same magnitude. I may have drawn it a little bit shorter here, but the idea is that we're taking the same vector, but we are flipping its direction. We are going in the opposite direction as if we were kind of flipping it over the origin 180 degrees. So negative v is the same vector, but going in the opposite direction. If that is the case, if I'm going vector u minus v, then from the tail end or the terminal point of u, I would want to do my best to draw a vector going in the opposite direction, so minus v this way. So that's what u minus v would look like. And again, that resultant vector, we start from the initial point of u going to the terminal point of negative v. So this would be u minus or u plus negative v. They're the same thing, u plus negative v. And would this work to be the same thing if we were to flip the order around? Well, if you were to write negative v plus u, then the answer would be yes. So what we could do from here is we could draw negative v. So again, I'm going to do it the second way just to kind of show that we're going this way. So negative u, here's negative u, and let me draw negative v, again with a dotted line. Doesn't matter too much since I'm labeling everything. And that's not really perfectly parallel. I'm trying to do my best to make it parallel here. But from the tail end of negative v, oh, I mislabeled that as u, sorry about that. We got negative v plus u, and that would give me the same thing, same resultant vector up there. That would be negative v plus u there. And either one works to give you the same resultant vector. So there's vector subtraction. The final vector operation that I want to go over before I try a different practice problem with actual numbers is to do scalar multiplication. And all that means is to take a vector, and when you multiply it by a scalar, all you're doing is you're changing its length. So if k is some scalar, let's say, for example, k were equal to 2. Let me just do an example. Suppose you had some vector where your vector were, let's say u were equal to something like, I don't know, 2, let's say 2, 1. So vector u is 2, 1, for example. So it's got its initial point is at the origin, and I were to draw an x value of 2, a y value of 1. If k were equal to 2, then think about what that looks like. K times u would be equal to 2 times 2, 1. And all you're doing is just distributing that 2 to each one of those components. So k times u would just simply give you this resulting vector, 4, 2. And so on our end, what that looks like, let me just change the colors of that, k times u would be a vector that is going in the same direction. Its direction hasn't changed, but now it's twice as long as what we had before. So we had vector u, we multiplied it by 2, by the scalar 2. So now it's a vector going in the same direction, but it's twice as long. So that's what k times u would be. And I've already discussed that when we have a negative scalar, that negative flips that vector in the opposite direction, as we saw here. So to have a negative vector means we're going in the opposite direction. Let me try a problem where we're going to graph these vector operations, but mathematically we can also see what's going on. So I'll go ahead and just try something like C and, well, let's just start with A first, and I'll leave C and D to you. We'll go with A and B. So if vector v is negative 2, 5, what would 2v look like? Well, that just means we're going to take this vector v and we're going to multiply it by 2. So it's 2 times negative 2, 5. And so what that would give us is negative 4, positive 10. Right? If you know how to distribute numbers, then you can do these operations. All right? Let me go ahead and try B. So with B, we're doing W minus V. So W being 3, 4. So this is going to be 3, 4, that vector, that's W, minus V. Well, minus V. V is equal to negative 2, 5. Negative 2, 5. And we're going to subtract here. So we've got 3, 4. Now we're going to distribute that negative. So that's going to be equivalent to adding positive 4, negative 5. And if we add these up, we would say here that, oops, I went ahead and changed that to 4. Sorry about that. That would be 2. So this would give us 5, and this would give us negative 1. And graphically, what would this look like? Let me just make this a little smaller so I have some space to show you graphically what's happening here. So graphically, if we had our first vector w at 3, 4, so 3, 4, vector v would be this one. I'm going to just do it in this color so we can see. This is vector w. Vector w was 3, 4, and vector v was negative 2, 5. So let me go ahead and extend this out, negative 2, 5. So vector v would look like this. negative 2, 5. Well, what would W minus V look like? W minus V means I would take the vector W, and then from the tail end of W, I would draw negative V. So from the tail end of W, I would draw negative V, meaning I would draw something that looks like this. Okay, this is what negative V would look like. And this is just a sketch right now, but let's just see how close we got. Well, our final vector, W minus V, we see should look like this. There's W minus V, and we can see that we're actually pretty darn accurate. Our final answer was 5, negative 1. And this was just a rough sketch, but you get the idea. So we can see W minus V gives you a resultant vector W minus V that ends with the terminal point 5, negative 1. We see it mathematically here, and we can also see it graphically as we've drawn. So go ahead and try the remaining problems here, and I encourage you to practice sketching all the vector operations, as that is something that you will need to be responsible for.